This is our last recording of chapter 20, so this is going to be sections 20.15 to 20.17. We're going to talk about nucleophilic additions to one other kind of compound, and then we're going to look at retrosynthetic analysis and how we can do synthesis problems that are multi-step. So the last thing we're going to talk about adding to is what we call alpha, beta, unsaturated compounds. What these look like is a carbonyl that on the alpha position and the beta position has a double bond next to it. So this is a conjugated compound, so the electron density is delocalized over all four of these atoms. There's a carbonyl compound, a carbon, and the beta carbon, and they are both partially positive. So if we look at this, here we have our carbonyl carbon, partially positive because of the electron density of the oxygen and the electronegativity of it pulling from the carbon. And if we draw a resonance structure of this, you can see something that looks like this. Double bond here. And so, therefore, you have partial positive here because this is carbocation in this resonance structure. So our beta carbon and our carbonyl carbon are both partially positive. They're both going to be attractive to nucleophiles. So your nucleophile can add across either the carbonyl, which we call 1,2 addition, which makes an allylic alcohol, or your nucleophile can add at the beta carbon across the double bond, and that would be 1,4 addition, or conjugate addition, which makes a carbonyl. So let's talk about how that looks. If we have 1,2 addition, 1,2 addition has a mechanism like this. Your nucleophile comes in and adds to the carbon. The electrons go up on the oxygen. Now you have your R group still stuck on there. Oxygen, water, and a nucleophile. This oxygen can then be protonated by the water. And so you end up with an alcohol on the allylic position. It's done a 1,2 addition. One is the oxygen, 2 is the carbon. Out of our 4 system that has an oxygen and 3 carbons. If we want to talk about 1,4 addition, here's what it looks like. 1,4 addition has your nucleophile attack on the beta carbon. So there's your carbon. Nucleophile attacks on the beta carbon. Those electrons go over to the other carbon. There's your nucleophile. Now you have a negative charge here. This negative charge can then form a resonance structure that looks like this. So now you have a resonance structure where you have a double bond right next to the oxygen. Next thing that happens is protonation. That protonation happens from water just like it did for the other one. So there's your proton. Here you go. At the end of this step we have an alcohol, double bond, methyl-methyl nucleophile. You may recognize this structure. This is an enol. And what do enols do? They tautomerize. So here's our enol. And because we have OH minus in solution that was formed when we protonated the oxygen, it can tautomerize. So you're going to form this, and where you have the OH, you have a double bond O, and where you had a C double bond C, you no longer have a double bond. So there's your tautomerization. With organometallic reagents, which way the reaction goes is dependent on which reagent you use. So, organolithium and Grignard reagents form 1,2 products. Organocuprates form 1,4 products, which ends up being a carbonyl. And this one up here is an allylic alcohol. So those are our 2 possible products. So, summary of the reactions of organometallic reagents. We've seen them do a lot of things here. Let's talk about what our possibilities are. First one is that they attack electrophilic carbon atoms. Especially carbonyl carbons. Second thing we know is that after the organometallic reagent adds to the carbonyl, your final product depends on the presence or absence of a leaving group. So without a leaving group, you get an addition to make an alcohol. With a leaving group, you end up with nucleophilic substitution. And the polarity of the alkyl metal bond determines the reactivity of reagents. So if you have alkyl lithium and you have alkyl Grignard reagents, those are much more reactive than your alkyl cuprates. So there you go. Let's talk about. Make sure you think backwards. So where are good places to break bonds, and where could functionality be introduced? Those are the kind of things we're looking for. So let's do a practice problem. If we're going to do a retrosynthetic analysis. Say I want to synthesize this molecule and I want to do it only from 4 carbon alcohols. So, where am I going to look for functionality? Well, the functional group is that ketone there. So, I'm probably going to make a carbon-carbon bond here, or a carbon-carbon bond to the other side. If I break my carbon-carbon bond here, then I have 1, 2, 3, 4 carbons on this side, and 1, 2, 3, 4 carbons on this side. So I can make those from 4 carbon things. So let's break that bond. And we'll think backwards and we'll say, okay, I could have made this using a Grignard reagent. And it could have added to a ketone. Not totally, right? Because our product has a ketone in it. So we need an intermediate step. So that's how our carbons get together, but somehow we know after this step we're going to end up with an alcohol. So there's our alcohol. Here's our alcohol. And we can directly make an alcohol go to a ketone because we can oxidize it. And if we add these two pieces together, we can make this alcohol. So we're getting there. We have our 4 carbon groups, we have different things. We need to make both components that are needed for the Grignard reaction from 4 carbon alcohols. So let's talk about that. Here's our 2 pieces. We've got this piece here, and we have this piece here. This one we could have easily made from a 4 carbon alcohol by just oxidizing it. So here was our alcohol that we used. If we use PCC, it'll oxidize it to an aldehyde. If we want to make our Grignard reagent up here, we know we did that by adding magnesium and ether to something that looks like this, perhaps a bromine or a chlorine. And we know how to make that from an alcohol. If we have this be a chlorine, you can use this alcohol and SOCl2 to make it work. So ultimately, our starting materials look like this and this. We do simultaneous syntheses to make this piece and this piece, and then we put them together and oxidize our product. We're going to practice more of this in lectures so you can get the hang of how it works. But always what you want to do is look for functional groups and see how you could have added them or transformed them. This is the end of this lecture.